Hey guys, so welcome to our bit manipulation series. So in this series we are going to cover bit manipulation in details. We will understand what is bit manipulation, why it is so important to learn, and what are the kind of problems that we solve using bit manipulation. So this is basically an introduction video where we will understand what is bit manipulations and why it is so important. We will also understand some other bitwise operators that we use while solving bit manipulation problems. Okay, so let's start with the basic definition of bit manipulation. So bit manipulation is a technique of using bitwise operators to solve problems by working directly with the binary representation of numbers. So what we understand by this definition? So in bit manipulation technique, we directly get control over the binary representation of the data, and we perform certain operations to achieve the desired output. Okay, so I hope you understand this basic definition. So here's some important terms that we should understand is the bitwise operators and the binary representation. Okay, so we will cover this in details in this video as only. First, let's understand what is bit. So bit is basically the smallest unit of digital information. Okay, so what is bit? Bit is smallest unit of digital information. And how this is, and how we represent this digital information, we represent using 0 and 1. This is one bit and this is another bit. So whatever data that we store in the form of digital information are stored using the binary representation, and that representation is created using this bit 0 and 1. Let's understand what is 0 and what is 1. 0 is considered as a not set bit or an unset bit, where 1 is represented as a set bit. Okay, so why we have to understand or why we have to perform operations on this bit level? We have others number like decimal number, float, boolean. So these number also used to solve problems. Why we need to perform operations on bit levels? So the thing is, like, in bit level it is much fast. Okay, so our question is why bit manipulation? Okay, so the first thing that we will understand is it is much fast. Speed. Why? Because the operation that are performed at bit level is faster than arithmetic operations. Okay, don't go with spelling, it might be wrong. The second important thing is, like, it is space saving. Okay, how? You can use one integer to store multiple set using bits. Use one integer to store multiple states using bits. Okay, so I think you might be confused with this statement, how we are going to use one integer to store multiple state of bits. Don't worry, we are going to discuss this topic in detail in our upcoming videos. First, understand why it is important. So first, it is speed, it has space saving, and it is going to use to solve many complex DSA problems, which is important for your interview perspectives. So I hope you understand what is bit manipulation and why bit manipulation is important. Let's understand how we can represent any other decimal value in terms of bit or in terms of binary representation. Let's understand with one example. Let's say 13. So 13 is a decimal number, so its base is 10, and we have to represent in binary representation which base is 2. So convert a base 10 value to a base 2, we can perform a certain mathematical operations. So if we divide 13 by 2, it will be divisible by 6, and we will get a remainder of 1. Now again, if we divide the 6 by 2, it will be divisible by 3, and we will get a remainder of 0. Again, if we divide 3 by 2, it will give a remainder of 1. It will go by 1 and it will give us a remainder of 1. if we divide 1 by 2, it will be not divisible, so it will either go by 0, and at the end we will get a remainder of 1. So if we arrange this remainder from top to bottom, we will get a number 1101, and this is of base 2, which is the binary representation of 13. So I hope you understand how we can represent a decimal number into a binary number. And similarly, if you want to, let's say we want this binary number to convert it into decimal. Okay, so how we are going to convert it? This is, let's say, index 0, this is index 1, this is index 2, this is index 3. So to convert it, we have to multiply each by 2 and sum up. But before that, we have to give a power based on the index. So this is of index 0, this is of index 1, this is of index 2, and this is of index 3. So 2 to the power 0 will return us 1, and 1 multiplied by 1 is going to be 1. Here, if we sum up, anything multiplied by 0 is going to 0. 2 to the power 2, which is going to return us 4. And here 2 to the power 3 multiplied by 1, it is going to return us 8. So if we sum up all this value, we got our decimal value, which is 13 of base 10. So this is how we convert a decimal to a binary and a binary to decimal. I hope you understand this much. So far we have understood what is bit manipulation, what is bit, why bit manipulation is important, and how to convert a binary number to decimal or a decimal number to binary. Okay, so is this enough to start with our bit manipulation topic? No, we also need to understand one important key that is there in our definition is bitwise operators. So what is bitwise operators? So in all programming language, there are certain bitwise operators that is available to perform operations at bit levels. So these bitwise operators are bitwise AND, bitwise OR, bitwise XOR, bitwise NOT, left shift, and right shift. Okay, so let's understand each of them one by one in details. So let's start with our first, which is bitwise AND. It is represented by this symbol. So bitwise AND follow a rule that when both the value is 1, then it will return 1. What does it mean? It means, let's say we have two value A and B, and we are performing an AND operation between A and B. So if both the value is 1, and then we are going to perform AND operation between A and B, it is going to return us 1. Let's say the other condition, if A is 0 and B is 1, in that scenario if we perform AND operation, it is going to return us 0. Let's say in another scenario where A is 1 and B is 0, then also it is going to return us 0. And if A is 0 and B is 0, then also it is going to return us 0. So this is the rule that AND operation perform, that both the bit must be a set bit. Let's understand this with an example. Let's say 5 and 3. So the binary representation of 5 is 0 1 0 1, and the binary representation of 3 is 0 0 1 1. Okay, so if we perform an AND operation here, 1 and 1, it means it is going to return us 1 based on our rule. 1 and 1, it is going to return us 1. If any bit is an unset bit, it is going to return us 0. If any bit is unset bit, it is going to return us 0. So this is the output of the operation 5 and 3, and the binary representation is this, and if you convert it into decimal, it is going to be 1. So and 5 and 3 is going to return us a value 1. So I hope you understand what is bitwise AND. Let's go to our next, which is bitwise OR. It is denoted by a pipe symbol. So in bitwise OR, let's understand with a similar example. We have two value A and B, and we want to perform OR operation between A and B. So if both bit are set bit, so in bitwise OR, at least one bit should be a set bit. If both bit are set bit, it means at least one bit are set bit. It is satisfying the condition. It is going to return us 1. Let's say if this is 0 and this is 1, then also it is going to return us 1 because at least one bit is a set bit. Now the third condition is if a is 1 and b is 0, then also it is going to return us 1. The only condition where it is going to return us an unset bit when both the bit is unset bit. So this is the rule that we are going to follow when we perform our operations. Let's understand with the same example, 5 or 3. So 5 is represented by 0 1 0 1, 3 is represented by 0 1 0 0 1 1, and we perform AND operation. If both bits are set bit, it is going to return us 1. If at least one bit is set bit, it is going to return us 1. It is again going to return us 1. Here both bits are not set bit, it is going to return us 0. So this is the binary representation of the value that we are going to get as an output of the operation 5 or 3, and if we convert it into decimal value, it is 7. So I hope you understand these two operations, how you perform bitwise AND and bitwise OR. Let's jump into the third bitwise operators, which is bitwise XOR. So bitwise XOR, it is denoted by this cap symbol. So the rule here is it is going to return us 1 only if the bits are different. Okay, so what rule this bitwise operators follow? Let's say we have a value a and b and we want to perform a XOR b. Let's start. If a is 0 and b is also 0, so at least one bit should be different. If both are same, it is going to return us it is going to return us 0. Now let's say a is 1 and b is 0. See, at least one only, it is going to return us 1 when the bits are different. Here the bits are different, so it is going to return us 1. Here let's say a is 0 and b is 1. Again, it is following the rule. If two bits are different, it is going to return us 1. Now let's say if a is 1 and b is also 1, in that scenario it is going to return us 0, because the rule is there should be at least different between a and b. Okay, so if both values are same, it is going to return us 0. So this is the rule that XOR operation follow. Let's understand with the same example, 5 XOR 3. So 5 is represented as 0 1 0 1, 3 is represented as 0 0 1 1. If both bits are set bit or same bit, it is going to return us 0. At least both bits are different, it is going to return us 1. Both bits are different, it is going to return us 1. If both bits are same, it is going to return us 0. So this is the output, and if we convert it into decimal form, it is going to give us 6. Okay, so I hope you understood this bitwise XOR. Bitwise operator that we are going to understand is bitwise NOT, which is denoted by this symbol. So let's understand this with one example. So let's take 5. If we represent 5 in terms of 8-bit, let's say starting bits are 0, and if we represent 5, it is 0 1 0 1. Okay, so this is 5. If we apply a NOT operation, NOT, what operators basically do is it flip all the bits. If the bit is 1, it will convert to 0, and if the bit is 0, it will convert to 1. Okay, this is the simple rule that bitwise NOT operation perform. So if we flip all the bits of 5, we are going to get a value 0 1 0 1 1 1 1 and 1. Okay, so this is the value that we are going to get after performing a NOT operation on value 5, and this in decimal form it is represented as -6, because all the value in the starting we have, because the value in binary representation starting with 1, and this is represented as -6. To understand this, we have to understand the 2's complement. Okay, so let's take this same example and understand what is 2's complement. To find the decimal values of 2's complement negative number, we have to take this number as 1 1 1 1 0 1 0. Okay, now perform an invert bit, which is basically a NOT operation on it. If you perform NOT operation, we are going to get this value. Okay, once this is the step 1 of 2's complement. Now the second step is to add 1 here. This is the second step. Okay, if we add 1 here, 1 plus 1 will be 0, carry will be 1, here it is 1 and 1, and the remaining will be 0 as it is. So this is going to be our value after performing the 2's complement, and this value is nothing but 6. Okay, so this is represent as -6 in 2's complement. I hope you got the idea of 2's complement and how we are performing the bitwise NOT operators. Okay, so our next operator is left shift and right shift. Let's cover those two operators as well. So the next operators is left shift, which is denoted by 2 left arrow symbol. So the left shift or left bit operators, what it perform is it move each bit to left based on the number of shift we want to perform. It is very equivalent to multiplying a value by 2. Let's understand this with an example. Let's say we have to perform a left operation with one step on the value 5, so we will represent it as 5 left shift by 1. Okay, and the output is 10. Now let's understand how. If we see 5, it is 0 1 0 1. Okay, and the remaining value in front of this is 0. Now we are asking this value to left shift by 1. It means this value will left shift, 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 and all value will left shift by 1. So if we write this 1 here, 0 here, 1 here, this is an 8-bit value, so this one will come in place of this, and now we have remaining 40. Now what we will write in this place, which is created after shifting the value one place to left side, we will fill this value with 0. Now if we see this value in decimal form, it is nothing but 10. So this is equivalent to 5 multiplied by 2, which is equals to 10. So left shift is also used to multiply a value by 2. If you're not able to understand it, let's understand with one more example, which is 3. 3 is represented as 0 0 1 1. Okay, so if we left shift this 3 by 1, we will get 0 1 1 0, and that is nothing but 6. Correct? So I hope you understand how this left shift operator is performing its task. So now let's understand right shift. It is obviously denoted by this 2 arrow on the right side. So right shift is just like the left shift, which move the bits to the right side. Let's understand this with the same example. 5 right shift 1, and it is equivalent to dividing a value by 2. So if we perform 0 1 0 1, which is the binary representation of 5, and if we right shift all these value, we will get 0 0 1 0, because this one will go out of bound. Sorry, let's understand again. Okay, now we have a value 0 1 0 1. Okay, and here this is not out of our range, and here all the values are 0. Okay, and we are moving this to right shift, which means it is going out of our range. We are not going to consider this as a part of our number, and here in place of this we will write this 0, and instead of this 0 we will write this 1. This 0 will come in this place, and this remaining will be like this. So now if we see this number is nothing but 2. So how it is going to work? So if you see 5 divided by 2, which is equals to give us a 2 with a remainder of 1. Okay, so if we divide any number by 2, the value that we are going to get is 2. Sorry, if we divide the number 5, the value that we are going to get is two. So right shift is basically used to perform division operations, and the left shift is used to perform multiplication operation. There are other application also that is we can perform by using left shift and right shift that we are going to cover in our upcoming videos. So this is just an introduction video where we have covered what are bitwise operators and how they are used, what is bit manipulation, why it is important to understand. So that's it in this video. From the next video we are going to start solving some simple DSA problem using this bit manipulation and bitwise operation techniques. I hope you like this video. Thank you for watching.